Math 265A, that's Calculus 1, and we are Cuesta College. We are Cuesta College, yeah, I am Cuesta College. My name is Joe Vasta, and we're covering 4.9, which is antiderivatives. This lecture should be probably listened to after you do the lecture on the bug that we did. I think it was bug 12. So we probably already know how to find the answer to this if you were doing bug 12 with me. So let's go ahead and do this. It says find all, this is what your book will say, find all antiderivatives of the given function. So we remember that the derivative is just one thing, but when you go to do the antiderivative, there's going to be infinitely many things. And I'm kind of being vague, so we can go ahead and write that so I don't give you the answer. So you could pause the video and see if you can do this problem. Okay, so how am I going to write the antiderivative? I mean, we have a prime for the derivative, but this guy right here is already the derivative. So what a lot of calculus books do at this stage, and we're not going to do this notation that much, but we'll do it here in the next few problems, is the antiderivative, if the function is this, f of x, the antiderivative, they'll make the capital letter. So capital F of x will be our antiderivative. Okay, so that, we're going to do the power rule. Here's a 3, here's an x, here's, we add 1 to that 4, so that's a 5, and then we divide by 5. And so our antiderivative looks like this. 3, I don't know why I'm writing it again, by the way, but there it is. Now we forgot something, and we talked about this on bug 12, is that 3x to the 5th over 5, if you take its derivative, you end up getting, 5 times 3 times x to the 4th over 5, and the 5's cancel, and you get 3x to the 4th. But if you did this thing plus 1, you would still get 3x to the 4th. In fact, you did it any constant, because the derivative of a constant is 0. Gives you it. So I'll put the constant up there. This right here is the antiderivative. It's a family of functions where you take the derivative of any one of those family members, and there's infinitely many of them, you end up getting this function. Okay, so this is what we're doing in 4.9. We're learning about antiderivatives, and what I'm going to do, and I'll include this in the PDFs that's next to the video on the website, is, well, let's take a look at some derivative rules and some antiderivative rules. So you have a function called y. Y prime is the derivative. So with the antiderivative rules, I just switch them around. So y prime is there, and then y is the antiderivative. Okay, f prime, g prime. Now if I end up calling these functions f and g, just like I did on problem number 1, I called that little f, then the antiderivative, sometimes we can write this as capital F, and same with g, we'll call it capital G. Now here's the deal, if you have a constant times a function, we take the derivative of that, it's just going to be the constant times the derivative. Well, if you go back, the same rule is going to apply, and we were using this rule on bug 12. So the antiderivative of constant times a function is constant times the antiderivative. And same with the sum rule. The sum rule applies for antiderivatives, and the difference rule applies for antiderivatives. What about the product rule? Well, actually, I do not have a product rule here. Now, could it be filled in later? Yeah, there's something called integration by parts, which we are not doing in this class. And same with the quotient rule, we do not have anything that we can write there for now. The chain rule, well, what do I write here? Nothing. We don't want to make it complicated, but the chain rule is going to be a U substitution, which we will learn at the very end of this class. The derivative of a constant is 0. The antiderivative of 0 is a constant. Okay, let's move on to the next set of rules, and we'll put them all together on one piece of paper after we go through these. So here's y, y prime, y prime, y. So here's the power rule, and we kind of went over this on bug 12, x to the n. And now if we want to take the antiderivative of x to the n, we end up getting the formula that we were writing down. This one is actually not included in this section, but I'll put it here anyway. The derivative of b to the x is b to the x ln b. And the antiderivative of b to the x, it looks like b to the x over ln b plus c. So what happens if you want to go back, this right here is just a constant. And so when you go back, if this thing wasn't here, this constant wasn't here, then it would actually be on the bottom of that. And so that's what we're saying. This one's the simplest. The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x plus c. For these logs, we don't have any formulas right now that we're going to put. In fact, this one, the formula is going to be on this one. So we may have seen in this class that you have the ln of the absolute value of x. You take the derivative, it's 1 over x. So when we take the antiderivative of 1 over x, we're not just going to write ln x plus c, because 1 over x's domain is everywhere except 0. And so if I just wrote ln x, I'd be leaving off half of the graph. So it's going to be ln absolute value x plus c, so we're going off this one. So we're going to have to remember, these are things that you should remember, but it's just one of those things when you walk into Calculus 2, your teacher's going to expect you to know some of these things. Let's go ahead and take a look at a few more. I know I'm hitting you with lots of rules, but I'd rather hit you with the rules, and then we can kind of go over these rules as we do examples. Here were all 6 trig functions. And so look at this. The derivative of sine is the cosine, so the antiderivative of cosine is the sine plus c. Now we have the derivative of cosine is negative sine, which means the antiderivative of sine is negative cosine. So now when you take the antiderivative of the sine, which was always the positive one, when you take the derivative, it's a negative cosine. So look at these other ones here. These are just the results of the derivative rules. Okay, I'm not going to verbally say them all, but you can take a look at them. Something happened on this one where things wouldn't fit, so I had to write derivatives and antiderivatives. I didn't put the rule part there. And so here are the 6 inverse trig functions, and really most calculus books will only grab on to the secant, the tangent, and the sine. So like the antiderivative of this guy right here is sine inverse plus c. What's kind of funny, because we don't have that one, because if you put that on the list, it would look like this, except there would be a negative. And so we don't really need to put that on the list. If there was a negative in front of that one, like we have here, I would just say negative sine inverse plus c. And so we have the tangent inverse. You know, we have 1 plus 1 over x squared, and then this guy right here. Okay, so wow, that was a lot. Let's go ahead and show you how many of these things there are. And some of them are kind of cheap. You know, you're not really, you know, these ones were probably obvious and we were doing them. So really the significant ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and those are some antiderivative rules. We'll be using those antiderivative rules as we do some problems. What were the instructions? Find all antiderivatives of the given function. So let's go ahead and do problem number 2. So in your homework, it's going to look like I assigned a ton of homework. A lot of the homework will go fast. So the antiderivative of this we'll call f of x with a capital F. And so the antiderivative of e to the x is just e to the x. So what is this going to be? This is going to be 5 e to the x. And don't forget, plus c. So that's why I probably put 3 of them on one paper, because it would be, I'd really be wasting paper. It would be obvious. Okay, find the antiderivative of 3 cosine x. Okay, so this is going to be f of x, and these things should be memorized because you're going to be using them all over the place in future classes. So if you look at the chart or whatever, you remember, you know, you could always do the derivative of this and check your answer by doing that. So the antiderivative of the cosine is actually the sine. So this is going to be 3 sine x plus c. So look, the derivative, if you want to check it, of sine is the cosine, and so that's what you have. The derivative of a constant is 0. This guy right here, that guy right here, use just this one right here. So all we're doing is, you know, doing some things that we see on the list. And that's what they'll do in your homework, okay? So we have f of x equals the sine inverse x plus c. Let's go ahead and do another problem. This problem is going to be pretty simple, but we're going to introduce some notation and definitions with this. So this is problem number 5. The antiderivative happens to be 2, and then this is really x to the 1. So we're going to add 1 to that exponent, so this is going to be 2x squared and divide by 2. So the antiderivative of this is x squared. And you can verify it if you took the derivative of x squared. Oh, and I forgot to put, see, now look, I forgot to put the plus c. Good job. Okay, so there's the plus c right there. Okay, now we are finished with this problem. Let's talk a little about notation. Okay, for derivatives, we had notation like, okay, so this is x squared. Let's just put plus c. If I wanted to hit that with the derivative, I would, sometimes you hear me call this the derivative gun. You put the derivative gun in the front and go, and it gives me the derivative. The derivative is 2x plus 0. So is there notation like this for the antiderivative? And there is notation. So we took the antiderivative of that. So this is going to freak you out. Here's your antiderivative gun. It looks like this. Now, with that antiderivative gun, you can't just put that there. This derivative gun requires that you have to put a charge on the other side of the function you're taking the antiderivative of. So here's your charge, dx. I know that's really weird, but these signs, this integral sign and I said something weird, integral, this sign here, which looks like a stretched out S, and there's a reason for that, and we'll find that out in chapter 5. And this guy right here, they always go together. And so that is the notation, just like d dx is the notation for derivatives. And we end up getting x squared plus c. Okay, let's get down a little bit more to what things are. This guy right here, that whole thing on the left-hand side of that equation is called the indefinite integral. So let me write that down. So this is an integral, okay? And it's an indefinite. There's two kinds. There's a definite integral, and we don't know what that is, but this is the indefinite integral. So whenever you see a stretchy S, you're looking at integration. And integration is another way of saying anti-differentiation. Okay, so we have this right here. That has a name. This function here that you're trying to take the integral of is called the integrand. And this guy right here, we already know what that's called, but I'm going to go ahead and tell you this is called the differential. And the differential tells you what letter you're integrating with respect to, or taking the antiderivative with respect to. You're taking the antiderivative with respect to x. Now, if some of you make it to multivariable calculus, you may have a few letters like x's and y's inside the integrand, and then the differential should be written there because it will tell you what you're taking the antiderivative with respect to, and you treat all the other letters as constants. Now, if what I just said went over your head, that's all right. So x is the independent variable. But it also has another name here. It's called the variable of integration. Variable of integration. Okay. And so your book's going to ask you to find or determine the indefinite integral. And And that is just the fancy way of, that means they're going to give you the stretchy s in this differential. That's the fancy way of saying find the antiderivative, okay, which is a whole family of functions. So when you're doing your homework, they'll like change the directions and the notation may change, but you're kind of doing the same thing. And so look what I mean right here. It says determine the indefinite integral. Another way to say this is to find the antiderivative. Another way of saying what we're going to do is integrate. So that's what we're doing. We're going to integrate this function. Now, if you're looking at your rules of derivatives and antiderivatives, you don't see anything like this in there. So this one looks like it's going to be a little tougher. Let's go ahead and rewrite it. What I'm going to do is I'm going to do a little algebra to make it so we can take the antiderivative. I'm going to split the fraction. So this is going to be 6 over x squared minus x over x squared plus 3x squared over x squared. I'm going to put some parentheses up because now I have more than one term, and I'm going to look at that. I'm going to analyze that. Okay, so this is going to be the integral of 6. I'm going to bring that cross the line, change the sign, and make it be 6 times x to the negative 2 power. This one, when you do that, you end up getting minus x to the negative 1 power. And then over here, we're going to get plus 3. So notice I always have to put this stretchy s, and I have to put the little charge, the differential. So in order to use this gun, you see your function that you want to zap with the antiderivative gun. It's more complicated than your derivative gun because you have to somehow maybe get a friend or something to put the charge on the other side, and then your gun will work. Now when you go to do the power rule, you're going to find that this one, you know, if you go to do that, you know, you're going to go, oh, look at this one right here. You're going to, let's put it up here. You know, so lots of people will do this, and they'll do the antiderivative of this. Okay, so there's the notation, and they'll say, oh, I add 1 to that, and then I go like this. Uh-oh, something happened. Okay, so this right here is bad. So what we should do is recognize that this guy right here is really 1 over x. And 1 over x happens to be a special thing on our rules. Let's see if I can find, lost all the rules here. There it is, 1 over x. So that's the one time you can't do this rule with real numbers. This is the ln absolute value x. Okay. So let's go ahead and, you know what, I think I can finish this problem on this piece of paper. So here it goes. I'm going to zap each of these 3 things because we have the antiderivative of a sum is the sum of the antiderivative. So I'll just do these one at a time, just like I would do derivatives. So the antiderivative of 6x to the negative 2. This is 6x, and you add 1 to that exponent. So negative 2 plus 1 is negative 1. Okay, now what I have is I have to divide that by that negative 1 as well, because that is the power rule for antiderivatives. The next one's going to be minus, because the minus is there, 1 over x. The antiderivative of 1 over x is ln absolute value x. The antiderivative of 3 is 3x. And don't forget plus c. So I'm going to clean this up just by writing one more step. This is going to be negative 6 over x. So this negative is the negative that's there. 6 over x. Then we have minus ln absolute value of x plus 3x plus c. This right here is the antiderivative of this function in here. In fact, this is the indefinite integral. We've just found it. And it's a family of functions. See the C there? And if I went and hit this with the derivative gun, I would end up getting probably something that looks like this, or, you know, I mean, but I could get this right here if I hit it with the derivative gun and found a common denominator. So that is evaluating or determining an indefinite integral. Let's go ahead and try a few more of these things and see how we go. And this is what you do in your homework. The only way you're going to get better at this is by doing your homework. Okay, the next one. So we have 12 cube root of x. We're taking the integral, or we are determining the indefinite integral. But sometimes you say you're taking the integral when you do this. And so what we want to do is, we don't see the cube root in the rules of antiderivatives. But this is just like derivatives in the sense that when you see a cube root or a square root, you want to write that as a power. So this is going to be 12x to the 1/3 power. Okay, so now I'm going to go ahead and do that power rule for antiderivatives. So it's time to zap this function with the antiderivative gun. We have 12x. What's 1/3 plus 1? It's going to be 4/3. And we really want to write it as 4/3. We don't want to write it as 1 1/3, because what you have to do with that 4/3 is put it on the bottom. And of course, this is going to be plus c. Okay, so now something interesting is going to happen when that's on the bottom. We're going to do a copy dot flip. So here's copy dot, and then we flip that. So this is going to end up being 3/4 plus c. So sometimes when you do a lot of these, you just start ending up writing the 3/4, but I wouldn't recommend it at first. So what happens here? The 4 and the 12 will reduce, so this will give me 3, 1, and the final result, I think, is going to be 3 times 3, so that's 9x to the 4/3 power plus c. And if you're kind of like, I don't know if that's the right answer, then go ahead and take the derivative. That's what I'm going to do. So your homework might tell you in some of the problems to check by taking the derivative. So we're going to check by taking the derivative. Let's just say that this is y equals 9x to the 4/3 plus c. So what I'm going to do here is I'm going to go y prime equals, I have the 9 there, the 4/3 jumps out front, 4/3 x to the, now I subtract 1, I get 1/3. This is going to be plus 0. And now I'm going to go ahead and see if we can reduce some things. The 9 over the 3 becomes the 3 over 1. This becomes 12 x to the 1/3, and then 0's out of there, which is really 12 times the cube root of x. Check, we got the right answer. And so that is how you crank out these problems. We'll do a few more of these problems to make sure you feel all right with your homework. So problem number 3. Problem number 3 looks like a mess. So once again, you go to the antiderivative rules and you don't see anything, you know, on the left-hand side here, that looks quite like that. So you're going to use some algebra and maybe some trig to clean things up. So let's go ahead and split our fraction. 5 sine x over the cosine squared x minus 8 over the cosine squared x. And we have two terms, so I'll put parentheses and a dx. Now, this is when we want to know our trig. So when I have a sine over a cosine squared, that is the same as having a 1 over cosine times sine over cosine. Now 1 over cosine happens to be the secant of x, and the sine over the cosine is the tangent of x. So this thing right here, this first term, becomes 5 secant x tangent x. Now the second term, we have to know what 1 over cosine is. So 1 over cosine is the secant x. 1 over cosine squared is the secant squared x. So when we have 8 over cosine squared, we end up getting 8 times the secant squared x dx. Okay, so now at this point, and once again, these are things you should try to memorize. You see the secant tangent right there, which the antiderivative is the secant, and you see the secant squared where the antiderivative is the tangent. So let's go ahead and write out our answer. We have 5, and so the antiderivative of secant tangent is secant, so it's 5 secant x minus 8. The antiderivative of secant squared is tangent x. And don't forget your plus c. And that gives you the answer that we're looking for. Let's go ahead and do another problem. And maybe you want to pause the video and see if you can do this problem on your own. Okay, problem number 4. What am I going to do? Because I look at my antiderivative sheet and I don't see anything that looks like 3 over 4x squared plus 4. I mean, look at that. I don't see anything. I see 1 over x, but that doesn't look good. And then, oh, but I see these things here. I see an x squared plus 1, and here's a 1 plus x squared, and both of those have 4. So I'm going to do some algebra here, and we'll factor out maybe a 4 on the bottom. So look at this. We have a 3 over 4, and then we have an x squared plus 1. This is dx. Now here's something I'm going to show you. I don't know if they do this in this section or not, but you have a 3. Did you know that you could actually write the 3 out in front of the integral sign? It's called taking it outside or factoring it out. And same with the 4. So I can write that 3/4 outside that stretchy s, and now I have 1 over x squared plus 1. That's one term, so I'm not going to put parentheses, and I have a dx. Some books will sometimes put the dx on top of the fraction. And then look at that. That is the one that's on the sheet. It says 1 over, oh, you might say, oh, it's not, but you can rearrange the bottom, the denominator. And so this is going to be the integral of 1 over x squared plus 1 is the tangent inverse x. And don't forget the 3/4 or the plus c at the end. So this is 3/4 tangent inverse x plus c. Now some books will call the tangent inverse arctan, okay? And arctan is good to know that, ARC tan, because if you're doing a graphing program like Desmos or whatever, that's going to be the thing you probably write. Let's go ahead and do another problem. I want to see if you can do this problem on your own. Pause the video. Okay, so how do we do this? You're looking at your antiderivative sheet and you go, I don't see anything like this. What you have to do is you have to multiply that out using algebra. So I'll do that off to the side. So x times x plus 1 squared. I'm going to go x plus 1 times x plus 1. And I'm going to go x times. We FOIL. First outside, inside, last. So I have x squared plus 2x plus 1, which gives me x cubed plus 2x squared plus x. So that is what this integrand equals. So this is going to equal the integral of x cubed plus 2x squared plus x looks like that. Okay, so now what I'm going to do is I'm going to now hit each of those with the antiderivative gun using the power rule. The first one's going to be an x to the 4th over 4 plus. The next one's going to be a 2x, add 1 to each of those powers, 3 over 3 plus, this one's going to be x squared over 2 plus c. And there's the answer. So I had to do a little algebra to get to the answer. Some books, let me just write it in a more positive color than red, will write their answers like this, like 1/4 x to the 4th plus 2/3 x cubed plus 1/2 x squared plus c. So some books will write, and this is acceptable as well. Okay, so we have problem number 6, which asks us to find the solution of the initial value problem. Okay, so we mentioned this before in bug 12. This right here is called an initial condition. And we could have already did these problems in bug 12 because we gave you a velocity function and an initial condition, and you were to find the position function. So what we're going to do here is we are also going to circle this. This right here is the function you're starting with, and it has a derivative there. Sometimes you can think of this, and I might as well just tell you this now, as a differential equation. You'll be seeing differential equations in the next semester of calculus, and you might even take a differential equations class. So a differential equation looks like this. This is a simple one where there's an f prime, sometimes they call this y prime, equals 2 sine x plus 4x, and we are trying to find its antiderivative and solve this. So when they ask you to find the solution of an initial value problem, that's a problem that has a differential equation, or this, f prime equals this, and an initial condition. So since we've already done these problems in bug 12, hopefully the only dramatic part about this is the trig. So I'm going to go find the antiderivative, and it's true I can use the stretchy s, that integral sign, and the dx, but I don't need to use it here. I'm going to go ahead and say, well, what is the antiderivative of sine? It is negative cosine. So I have negative 2 cosine x plus the antiderivative of 4x. This would be x squared over 2. So it's really going, the 2 and the 4 are going to cancel a little, and you're going to get 2x squared plus the constant. Okay, so now what we want to do is this initial condition, f of 0 equals 1. We're going to plug that in there. So remember, f of x is really just y. This equals negative 2 cosine x plus 2x squared plus c. This initial condition is saying that x equals 0, so, you know, because it says f of x, but this is 0, when y equals 1. So we're going to plug that in here. 1 equals negative 2 cosine of 0 plus 2 times 0 squared plus c. So this initial condition is given, so we can find out what c is. Now the cosine of 0, that is going to be 1. So I have negative 2 times 1, that is 0. We have plus c, so 1 equals negative 2 plus c. c equals 3. So our final answer, when they ask us to find the solution of the initial value problem, is going to be this right here. F of x equals negative 2 cosine x plus 2x squared, and then plus c, so plus 3. And essentially what we have found the position function with a velocity function that was given and an initial condition. So that is the answer to what this problem asks us to do. Let's go ahead and do our last problem from this section, and it is problem number 7. So there it is. Coyote is propelled upward at a velocity of 20 meters per second. So they're going to use meters in the 4 problems that I assigned. Oh, so he's propelled upward at that velocity from the side of a cliff at an elevation 300 meters. So they ask us to find the velocity of the object for all relevant times. That's kind of a weird thing that the book puts there. I mean, find the velocity of the object or find the velocity function is actually a more standard way of asking this. But, you know, I put that in there because to show you that, you know, that's what the book says. Find the position of the object for all relevant times. What time? Find the time when the object reaches its highest point. What is the height? Find the time when the object strikes the ground. Okay, so this is quite an interesting problem. We've done physics problems in here, but now we're not really giving you the height function or the position function. We're just giving you this information here. So I'm going to go ahead and draw this information here. What are we going to do? We're going to draw a cliff. Looks like that. And Coyote, he probably propelled himself. So there's the Coyote. And he goes, and he's going to go up, splat. So that's what's going to happen with a velocity. So when they say propelled upward at a velocity, sometimes people call this the initial velocity, which is 20 meters per second. And the side of the cliff has an elevation of 300 meters. So there's the picture. And we are to find the velocity of the object and the position of the object. I'm going to go move this out of the way so we can do some of the problems that we're asked to do. Okay, so we have a gravity constant, and it all depends whether you're using meters or feet, but it's the same, you know, in terms of the gravity constant on Earth in the United States is the same as in Europe or in China. And for meters, it's going to be 9.8 meters per second. But we are actually going to be looking at when something's traveling down, we're going to call that negative. So with the problems that I assigned, you're always going to start off, because these problems are based on Earth and they have meters in them, with the acceleration of an object being constant. And the constant, when you're using meters and seconds, is going to be negative 9.8 meters per second squared. So the acceleration is the change of rate of the velocity. So this is just a constant. And that's how we're going to start off all the problems. Okay, so they wanted the velocity of the object. To get the velocity, I'm going to take out my antiderivative gun and hit that with the antiderivative. The antiderivative of a constant, we've done this many times, it's going to be that constant times x. But in this case, we're going to go ahead and use t. And then we have to put plus c. Okay, so here is our velocity function. And we are given an initial velocity. When they tell you the starting velocity, they're basically telling you that at time 0, the velocity was 20. So we are going to plug that into here. I mean, you can say v is 20 when t is 0. In any case, you'll have a 20 there for v, and then your time is 0. Now when people do a lot of these, they already know, they skip some steps and they can write down the velocity function when they actually look at what the initial velocity is. Well, in any case, you get 20 equals the constant. And so the velocity of the object for all relevant times equals negative 9.8 t. So I'm rewriting this one up here. Plus c. So plus 20. So this answers part A. Now, if the coyote was propelled downward with a downward velocity, then, and the downward velocity was 20, or the speed of that was 20, then you would have to put a negative if the initial velocity was negative 20, and then, you would end up getting maybe minus 20 there. Okay, the next question was to find the position of the object. So what am I going to do with the velocity function? I'm going to, so this is part B, take the antiderivative. So s of t is the position, and the antiderivative, this is going to be negative 9.8 t squared over 2 plus 20t plus a constant. Now, it's not going to be the same constant as above, so I'm going to make this constant be blue c, kind of like I was doing before in another video maybe, or was it this video? I don't know. It's all running together in my head. So what do we have here? We have s of t equals, well, 9.8 divided by 2 is 4.9, so this is going to be 4.9 t squared plus 20t plus c. Okay, so here's the deal. We have to find that c, but we're also given the initial height. So this is really the position function, or sometimes called the height function, and the initial height, that's the height at time 0, was 300. That's the height of the cliff. Okay, 300 meters. So we're going to go ahead and plug that into this. So, oh, I used an S. I actually should use an S. Okay, so I'm calling it the height. We have to stick with what? We don't want to switch around the function name, so this is S of 0. Okay, so we could say that S equals 300 when time is 0. So that's what I'm going to do. S equals 300. This guy right here is S when the time is 0. So you end up getting 300 equals C. Okay, so looks like we can now rewrite this equation here, this position of the function above the ground. So we have S of t equals negative 4.9 t squared plus 20t plus 300. This gives me the answer for part B, which is find the position of the object for all relevant times. Okay, now I'm going to go ahead and jot down the velocity here because I want to just use this piece of paper here. So the velocity is negative 9.8 times t plus 20. Okay, so here's the results here. And actually, I just copied it down, but if you took this derivative, you would get that. And a little diagram that I drew earlier is you take the derivative of the position, you get the velocity, you take the derivative of the velocity, you get the acceleration. Then you take the antiderivative, and this is what we did. We went this way, and then we took the antiderivative once again. I'm hesitating writing an A there for antiderivative, because then, you know, you might think, that's the acceleration. So we'll just do it that way. That's what we've done. We used, so when you're going back, you have to use initial conditions to get the specific functions for those. When going the other way, this is when we first learned derivatives, we didn't need initial conditions, and we were able to get velocity and acceleration just in a snap. Okay, part C. Part C asks this: find the time when the object reaches its highest point. So the time when the object reaches its highest point, the velocity here is positive, but it's slowing down, and then right here is the highest point. That's when the velocity is 0. And then after that, the velocity is always negative, and it's increasing until it hits the ground. So let's go ahead and find the time when the object reaches its highest point. We said that's when the velocity is 0. So that's when v of t equals 0. So that's when negative 9.8 t plus 20 equals 0. Add 9.8 t to both sides. So t equals 20 divided by 9.8. And so, I've done these calculations before. Oh, here's my calculator. So 20 divided by 9.8. And so this, we're going to round. So on this, I'm going to adjust things. I'll say, let's say all of our answers are going to be 2 decimal places when we're asked to round, which will probably be on C and D. Okay. So when I do this, I'm getting 2.0408. So this is going to be approximately equal to 2.04 seconds. So that's the time that it reaches its highest point. Well, let's go ahead and answer the second part of part C. It says, what is the height? Well, how do you find the height when you have 2.04? You plug it into the position. So this is S of 2.04 equals negative 4.9 2.04 squared plus 20 times 2.04 plus 300. And what I'm getting for that is negative 4.9 2.04 squared plus 20 times 2.04 plus 300. So this is giving me 320.4081. So it's going to be 0.41 since we're rounding to 2 decimal places. And this is, it says, what is the height? So we better put units on this. The height is not feet. The height is, there we go. The height is meters. Okay, so that answers part C. Now these are problems I think we've done before. When we started off with the position function, we probably asked what is the highest, but it's good to go over this again. I mean, this is an important thing. Okay, part D asks, find the time when the object strikes the ground. Actually, yeah, let's just do that. So when the object strikes the ground, we need the picture again. What does that tell you? Well, we're assuming when we do these problems where there's the ground, that when you're at ground level, it's going to be 0. That's not always going to be the case, but in this case, that we'll just assume that. So that's when the position is 0. So find the time when the object strikes the ground, we are going to be considering S of t equaling 0. And S of t is that guy right there. So negative 4.9 t squared plus 20t plus 300. We're going to set that equal to 0. I'm going to go ahead and multiply by a negative 1. So I have 4.9t squared minus 20t. This is just a style thing. I like to have this term in front of the t squared to be positive, but yeah, I mean, it doesn't matter if you keep it negative, because I am going to be throwing those numbers into the quadratic formula. The quadratic formula now will have, so this is the quadratic formula, minus b, so this is going to be 20 plus or minus the square root of b squared. So this is the square root of b squared. Looks like it's going to be 400. That's weird how I have that written there. Well, I'm going to go ahead and put minus 4ac. Okay, so when I go minus, let me just write this out. 4 times a times c. This is all over, that's going to be all over 2a. So 2 times 4.9. Okay, so you're going to be hearing me punching some buttons on my calculator. This is going to be 20 plus or minus square root of, okay, so I'm going to go 300 times 4.9 times 4 gives me 5880. The 300 is negative, so I wasn't very careful. There's a negative there, so this is going to be 400 plus 5880 all over 9.8. So this is going to be 20 plus or minus the square root, so plus 400 is 6280. This is all over 9.8. So this is going to give me 2 answers. So I'm putting this into the calculator. Square root. So hopefully I'm not pressing any wrong buttons here, because it's going on YouTube, and people are going to pass judgment on my button pushing skills. What I'm getting 10.127, so 13. And then let me go ahead and put a minus there. This is giving me negative 6.045, so we'll round to that. So it asked me to find the time when the object strikes the ground. Definitely is not going to be the negative time, because time started at 0. So the time that the object strikes the ground is going to be 10.13 seconds. And so we have been looking at antiderivatives. That completes this section. Have a good day.